Tick tock, tick tock, turn on record. There we go. Okay, all good. Now, we're in two replacement sessions for Thursday holidays here. And so, all good. It's most important for us to get this level foundation. And today is pretty much the last step of that, because we reviewed things that you should know from a previous class in operating systems, maybe some new stuff, but basically understand operating systems at the kind of kernel space level. And a previous class in introduction to networking, networks and networking, whatever anybody likes to call it, the basics of IPv4 and encapsulation and IP addresses and subnets. What we want to do today, again, is half of this. I'm certain you have a basic idea of how the DNS works, right? But there is the other aspect of core services for our network, which is called DHCP, Dynamic Host Configuration Protocol. And this is about assigning IP addresses. Like we talked about in the review to networking, we've got two sets of addresses that need to be in the packets in order to get our network to work and make it reliable. All right. Layer 2, we have the MAC address, which is, in the hardware on the network interface. The manufacturers have a system for guaranteeing that that is unique. And again, maybe we're surprised at how well it works, but it really does. All right. But IP addresses are assigned by system administrators, and that's why we have the concept of the broadcast domain and subnets, right, that we talked about before. So what we need today to talk about today is managing that and how we do dynamic assignment of IP addresses. Dynamic meaning that when any system connects to the network, we map an IP address that the network administrator assigns to that MAC address that is in the hardware. And that's the magic of DHCP, Dynamic Host Configuration Protocol. It's another client-server protocol that takes care of setting those basic network parameters that we need for configuring the network interface to just get the network to work. Then on top of that, we also have the domain name system. Nobody knows if it's DNS means domain name system or domain name service. Depending on the context, you can call it what you like. All right, but it's DNS, where we can put names to these addresses and map them in the same way. All right, so these two core services, these are the ones that, if you've had experience with Linux before on a single user machine, you've just been taking advantage of these services that someone else has spent their time and effort configuring and getting ready for us. But us, we them people, in SNA, we them people. And so we need to understand how this configuration works. For our TinyNet, most of it is ready, okay? Because there are hundreds of little decisions that need to be made about these things. And working with a good example shows us how to make those decisions. And so we don't have too much specifically to do with this, all right? But over time, we're going to come back to this again and again to just check and make sure that our subnets are coming up and everything's being configured properly, and adding in more domain names, okay, so that we can give one IP plus MAC address combination some different names, right? Because that's the magic of the system that we use on a daily basis. Every time we do something like this, we're taking advantage of somebody else's hard work to make this experience, yeah? It's user experience. So, and that's our goal. That's our goal, is to get the picture, understand what it takes to keep these services running, what it takes to provide us with the facilities that we use every day. Okay, I'm going to turn off the camera here. This one is another theoretical discussion, all right, straight from the PowerPoint, but bright and early tomorrow morning, we're going to get into the practical applications of this, which is why we needed the little special session today, right, to get everybody on the same page in our big group here. All right. So, two core services for the network. And again, we're exploring this because these are the services that we use on a daily basis. Right? And us, since we are focused on system and network administration, we need to understand how this works. So we saw this before. Hosts that act as clients and servers. Host is a kind of generic name in the literature, and so you can think of it as you like. Some people call them systems. We say host because it identifies individual machines. All right? Servers share resources with authorized clients. That's what our subnetting system is about. One of the things that we all know and can take for granted, all right, is this idea of names versus addresses. People like names because they spell things out. Computers, ouch, man, only work with bitstream. And so numbers are the natural representation. And so bridging this gap, this user interface gap, this user experience gap, requires a little bit of creativity. Well, a lot of clever people have worked on this for a long time now. But these definitions are the core ones back from 1970s, yeah? 1976, 1978, when people didn't know how networking worked. They had to invent it all by themselves. And so they came up with these definitions. A name identifies what you want as a string for people. An address identifies it in numbers. A closer representation to the bit string. And a root is just what we want to call a list of names or addresses that identifies these intermediate hops. That's what they're generally referred to. First hop, next hop, that sort of way. A way to get from one place to another, from a source to a destination is the way we usually think about it. So at boot time, and again, we discussed this when we talked about our review of network concepts. Since it's in the network interface hardware, at boot time, the system only knows its MAC address, right? But it doesn't know anything beyond that. That gives it capability to communicate within the Ethernet broadcast domain, but no more, right? We need more information to do more sophisticated things like global networking. And that means we need to know an IP address. Now, we can program this into the startup scripts, right? And indeed we do, because for in some circumstances, let's say it that way, in some circumstances, that makes the most sense to us as administrators. Most of the time, though, we want to use dynamic allocation, a client-server protocol, to automatically allocate this IP address. And again, this is what happens. It's so frequent now that we have ubiquitous wireless networking. This has become the standard way to do it. Anytime we reach a wireless access point and connect to it, we may get a different IP address that is mapped to or associated with the MAC address that's always there in our phone, our tab, our laptop, whatever hardware we're working with. It's the same thing that happens when we connect on our home wireless networks, right? There's some server at our internet service provider that is dynamically allocating us an IP address. When we get to that little Windows thing down here that says, you know, connect to a network that is within reach, okay? That means that we're trying to get an IP address on that particular network dynamically allocated to us. And the magic that makes that happen is called DHCP. Okay, a little bit of technical detail there. All right. So DHCP has been around for a long time because people have been facing this question for a long time. The old name for it was called BootP, for boot protocol. But, and again, in the community, we're very proud of our heritage. And so sometimes we still do see this name of BootP, but we still need to make that mental leap and say that's DHCP for us. And another old legacy part of this is these two ports, all right? I'm just going to put this in the meeting chat just for a minute, all right? Two ports are required for something that you may have heard about. MQA loves legacy technologies. Half duplex Ethernet that nobody's actually tried to use since the 1970s, maybe the early 80s, I don't know. DHCP and FTP are still supporting it. FTP is something that, again, people have pretty much given up, all right? But DHCP is an important one because it still uses half duplex, anything between the client and the server, all right? I'm sorry. Normally, for every other protocol that we talk about, all of the client to server messages and the server to client messages have the same port numbers in that TCP header. But DHCP and FTP still use two, right? One for server to client and one for client to server. And there's no practical reason for that except being proud of our heritage. And once people had it working, they decided, whoa, no point in changing it. No point in changing it. It's going to break somebody's system. And so we'll just maintain it and use it that way. So the idea here is, I mean, even back in the very first one, BOOTP, is that you get an IP address for a certain period of time, and they call that a lease. You know, just to give it a name that makes sense to people. Right? And that lease needs to be renewed. And the idea here is that with just a few IP addresses, we can serve a lot more people because the people who are offline don't need an IP address, and only the people who are online do need one. And so we have a pool of IP addresses, and you get one from the pool for a certain period of time. You can renew your claim on that, right? You can renew your claim on that as many times as the server will accept, and the server will work very hard to allow you to maintain that same IP address, right? But to move around from point to point, reconnect here, reconnect there, it's likely that your IP address is going to change because all of these IP address allocations are controlled by the system administrator for that particular network. So the DHCP server can also always assign, depending on how we configure it. And again, we'll look at this in practice on Thursday, all right? But the way we can configure it so that the DHCP server, when it gets a request in, will always respond the same way, or we can assign a random address from the pool that is available for that particular subnet. It's a four-part protocol, a four-step protocol. And again, the fundamental thing to remember is it works this way because when a system comes up on the network, all it knows is its MAC address. So the first thing it does is say, hey, somebody help me out. It sends a broadcast address that says, I'm new to this environment. Somebody help me out, right? Tell me how to communicate with the nearest gateway, right? And that's called a DHCP discover message. And if anybody is listening, a DHCP server, then they will send back a DHCP offer message that says, hey, I can give you this IP address for this period of time. What do you think? Right? And the client at this point can get multiple responses from different servers. And some way it picks. Right? We'll talk about that and the complications with that in a minute. All right? But somehow, if it gets more than one, it picks between them. If it gets just one, it's all clear. It sends back a request saying, yes, please, thank you, I'll take it. Right? And then the fourth part is the acknowledgement from the server that seals the deal, saying, yeah, you got it. I've updated my database and let's carry on having fun. So 2 up, 2 back, 2 on port 67, 2 on port 68. Now, this is a slide, this couple of slides, what I just said. All right, plus one more diagram here to give a little bit clearer idea of exactly what information is being exchanged. The offer, but remember the offer comes first, all right? And then the request comes back saying, yes, please, thank you, I'll accept your offer. You don't call it accept, they call it request. I don't know why. There's some additional information that can come along in this packet. And again, in practice, we'll see this and see how it works, because this is one of the key things that the TinyNet configuration uses to get the proper IP address for the subnet that we want the server on. And this looks very abstract, which it is, but when we see it in practice, I think it will kind of make a lot more sense, all right? But just this idea, keep this idea in mind. We'll come back to it tomorrow, right, when we're looking at it in practice. Some of those options, again, I think I've got another slide down here. Just let me disrupt the display a little bit. Oops, happened there. Hang on a second. Let me find the one I wanted to use here. Ah, here it is. Windows THC, Windows IP interface configuration. All right, that one's not it. Here you go. Here we go, this one. So if I go to Control Panel, Network and Internet, Network Connections, right-click on one interface or another, all right? It will show me what's happening here. And then I go to the properties and the IPv4. All right, we're not going to mess around with IPv6. All right, you can see that one here. IPv6 is there, but we don't have time to dig into that. All right. This is what we get. Obtain an IP address automatically or use the following IP address. This is the one that is a static configuration. But if you look at the one you're using now, it's going to have this spot checked, obtain an IP address automatically, which means get one from the DHCP. All right? And again, this one is going to be blank because you're going to use the DNS server, all right, that comes in the DHCP packet. If you look at the one you're using right now, your Wi-Fi interface, all right, this is going to look different because this spot is going to be checked and this is going to be filled in from processing the DHCP request, response, the offer and the request. This also is going to be filled in from the DHCP offer and request because it's in the DHCP options. And again, this is core network, and it works the same way in Windows as it works in Linux. All right, the DHCP options carry all of that extra information. Now, again, we want to mention this because there's a lot. If you look at the TinyNet documentation over and over again, it talks about turn off VirtualBox DHCP. That's a practical consideration that we'll get to tomorrow. But in principle and in theory, and to understand why we need to do that, all right, it goes back to the DHCP discover message. All right, DHCP discover, if I get two DHCP offers back from different DHCP servers, what do? I have to choose somehow which one I'm going to request. And the simplest way for that to happen is that it takes the one that came in first because it assumes that one is the faster one. All right. But this can cause problems for us as administrators because if somehow somebody gets in with what we would call a rogue or unauthorized DHCP server sending out those offers, and our clients start accepting those offers rather than the ones that they should, it messes up our network architecture. All right? So what we want to do is ensure that we only have one DHCP server responding when people put out those request messages that say, hey, I'm here, somebody help me out and give me an IP address. Again, that's why we need to take care of it. We'll look at how in practice tomorrow. Okay, so that's the rundown on DHCP. Again, I think you know basically how DNS works, right? when I put in, oops, stop that. That's not what I wanted to see. When I type my-tiny.net here in the address bar, all right, somehow that domain name needs to get translated to an IP address for the packets to move properly across the network. And that's what the DNS is for. All right. Now, in fact, again, you got to think about the theory and the practice. In fact, there's 3 places on our system where these names come into play, the name to address mapping. There's one file, and these are the Linux files that we'll be looking at, all right? There's one file called hostname that has the official hostname that we want put on the network. In Windows, this is stored in the registry. In Linux, it's in this file called etc hostname. There's another one, and again, etc is the folder or the directory in Linux speak, folder in Windows speak. etc hosts is different. etc hosts is for static mapping of an IP address to a name, okay? And, ouch, man, etc hosts, sorry, let me just jump back here one more time, because I'm a little disorganized here, all right? But there's a hosts file on Windows as well that uses the exact same format, all right? So that we can actually do this. All right, oh, sorry, let me just back up here. Here we go. All right. Local disk C, Windows System 32, drivers, etc. Check it out, you'll find it. Right? Because that's something that, again, is just core TCP/IP, right? That comes into Windows, comes into Linux, comes into Android. Right? If we look around, if we know what we're looking for, we can find it. Local, static, layer 3 addresses and names. Right? We refer to all the names as aliases, right? Because this is the official name of the host. And what we can do is we abstract a little bit and we map a new name to this name, right? And this name is the one that is actually mapped to the IP address. Sorry, I kept moving that around, but one. So this is the only official name, but we can have more than one name as long as we create a pointer to the official name and map the alias to that name. We can follow that chain through. So DNS, given a domain name, a DNS server will return a numeric IP address. That's what we call a normal DNS lookup. We call it normal to distinguish it from a reverse DNS lookup, where we say, here's an IP address. What names are associated with it? Right? That's actually an optional feature. Some people don't put it in because they want to keep that a secret. They're super paranoid, super security conscious, right? But most of the time, I won't even say normally, but I'll say most of the time, chances are you can get a DNS server. You give it an IP address, you can get it to give up some names that are associated with that IP address. So this is the part that maybe you're not so familiar with, right? Is that the whole system is a big distributed database. And again, the guys who designed this back in the day, back in the 70s, 78 to 84, 86, right, put a lot of thought and mental effort into developing this system. And they decided this whole system is going to work on what they call a zone of authority. So that when you get a domain name, you're completely responsible for the things that appear to the, let me get this right, I'm a little bit dyslexic, to the things that appear to the left, right? So there's a specific zone of responsibility that is MY. There's a specific zone of responsibility that is EDU MY. A specific zone, do I need to say it again? Specific for APU, all right? An APU is in charge of everything that comes to the left. AP space or whatever we have, all right? If I pick on this one, there's a .com and there is an office.com. And if I go to my email, for example, all right, I'm going to see new ones. I've got outlook.office.com versus www.office.com. All right, and that's all up to whoever owns office.com, which is, of course, Microsoft. Zones of authority. All right. There's no global map, right? Because each one is independent, and we call that delegation of authority. So let's focus on this little map right here. Right? Now, way up at the root domain is something called the dot. This is maintained by the Internet Corporation for Assigned Names and Numbers, ICANN. And they're in charge of deciding who gets to be in charge of all of these top-level domains. All right, and now there's a lot of these. All right, com, net, org, gov. All right, those are old ones, and there are many more now. All right, there's also like 200. Somebody asked me about this last time. I'll just put it down here. All right, MY equals Malaysia. TH Thailand. ID. ID is Indonesia. From a list of 2-letter country codes. A list of 2-letter, yeah. country codes maintained by the ISO. All right. Well, that's where we get .my, all right at this level. And then we get next level is .edu, .edu, .my, going back to the dot here, okay, or berkeley.edu, right, since it's in America, and the plain.edu is limited to universities in America. .com, pretty much global, all right, so Microsoft.com. But there's one group of people at this level who are in charge of everything. This is their zone of authority, right? And the root domain is the ultimate zone of authority. So the DNS servers at the root domain only keep track of everything in these top level domains. They keep track of the main server, the main domain name server for each top level domain. And then each top level domain, like com here, only keeps track of the people that are registered with it. Expedia.com, Microsoft.com, Google.com, Cloudflare, whatever, right? Same for net.org, whatever there. Once we register our domain name, like office.com, then we can designate as many or as few as we like, okay? Beyond that, to the left of that, in our domain name. So sales.microsoft.com used to be office.microsoft.com, but now it's teams.office.com, outlook.office.com, like that. But we're totally in charge of that. It's totally dependent on our name servers, okay, for anybody to be able to find it. And you know, this is again one of those things, when we look at it at this level, it seems so complicated, but it really just does work so smoothly, all right? Let's focus on this diagram here for a minute, all right? The way this actually works is when I put that URL, when I click on that URL, put it in the address bar, right? My browser sends a DNS query to the default name server, right? The one that was designated in the DHCP offer when I did the configuration, right? And it says, where is my-tiny.net or www.microsoft.com in this example. Sends it to that local DNS server. Now, that one is not shown here in the diagram, but has a cache here, a database with a time limit for each record, all right, that says this one is good for some hours, right? If it's not in the cache, what does it have to do? It has to start over from the beginning. And it contacts the root DNS server to say, give me an address for a .com server because I need to figure this out, right? And the root DNS server is the one that is authoritative for that domain. It's in its zone of authority. It only keeps track of the top level ones, .com, .th, .za, South Africa's one, all right? And it returns the address of the .com server. Then we've got to make a new query to the .com to say, give me an IP address for Microsoft.com or mytiny.net, if it's that one, right? And that address comes back. And then there's a third one that says, all right, Mr. Microsoft.com server, tell me an IP address for www.microsoft.com so I can slide that into the destination address of my IP part of the packet to go along with my own IP address from DHCP as the source part. And I can put in my own MAC address at the layer 2 source, and I can do an ARP query for the MAC address, for the destination MAC address, and we can get on with sending these packets. Again, when we look at it in the microscope here, it seems so complicated. We never believe it would actually work. But this is the way everything happens every time we access the internet on any one of our devices. It's really one of those minor miracles of modern technology. All right? So the point is you have to be invited to join the next one up on the domain hierarchy here. You have to make an arrangement to be delegated your zone of authority. And that's what it means to register a domain name, right? And if you register it, you get it for a while, but it's, same kind of model as DHCP. You have to renew your lease on that domain name every so often. And if you let it expire, it just goes back into the pool of available domain names, and somebody else can come along and pay the money and grab it up. MyTiny.net, I have to renew that one every 2-3 years. I remember. Don't remember which one, but I remember it's on Pearl Harbor Day. Okay, just one last thing. DNS is a unique protocol, all right, because of, again, the design characteristics. But this one, when we say it uses TCP or UDP, this is not to support a legacy networking technology. This is to support two different purposes. A normal domain name lookup, when we're doing this normal domain name lookup following this trail back and forth, all right? Basic fundamental design assumption is that this fits in a single IP packet, all right? So we don't need TCP to make the connection. It's just a single packet, and so we can use UDP protocol. If it gets lost, we can send it again and get it back. But when we've got a complicated system like Microsoft, all right, we've got a lot of servers that we're trying to keep track of, we want to make backups, all right? And so when we're making backups, we're transferring a whole set of information from one server to another about our zone. And for that purpose, we need to use TCP, all right? So the way that DNS works is that it's going to default to UDP. But if something doesn't come back over UDP, we'll time out waiting for that one, and then we'll send a TCP request because the response may be too big for a single packet. All right. So it uses one port, the well-known port, port 53, okay? But sometimes it will be using TCP. Normally, it's going to use UDP on that port. All right, I think that is sufficient, right, until we get to our practice tomorrow, all right? But again, what we're going to be doing tomorrow, and this is why for tomorrow, we will assume you have your 2-clone setup and configured to set up and configured to first things first. All right, there's 6 steps that we talked about last week on Thursday. All right. That's important because what we want to do tomorrow is talk about cloning that 2-clone machine. Right? And those first things first ones, if we don't do it before we clone, that means we have to do it 1, 2, 3, 4 times separately, which is too much work. You want to get that one done properly before we start replicating it as a bunch of other servers that we'll use on our network. And we've got standard configuration, pre-configuration. It's already done to have these on different subnets. We do that with the magic of DHCP, right? And it's done in advance. We don't have to do it ourselves because there's 150 to 1,000 decisions that we have to make, right? And it's better to have a good example to work with, right, than to go through all of that process ourselves each and every time. So this is what we'll be doing tomorrow, right? Is looking at how this pre-configuration is done, seeing how all of this fits together, okay? And getting our network up and running. But to do that the easy way, you need to have your 2-clone system properly prepared. Okay. That's good for today, right? We discovered yesterday that this is not going to give us a QR code. So never mind. Let's work through it anyway. We are, oops, oh, Schmidt. We are lab 3. So let's get our lab 3, not that lab 3. 2021-09-09-09, that's our lab 3, and today is the date. And we're in a lab session. Ooh, and then we started at, what time? 12:45, wasn't it? There we go. For 1 hour. And it's not going to give me a QR code. So, oh, it did give me a QR code. Didn't do that yesterday. Oh, thank you so much. All right. So, all good. Thank you so much for being here. We try to avoid this for the rest of the semester. Okay. And I don't see any reason that we cannot do that, because it's just important for us to keep in step March for the first half, because in some ways this is the hardest part, getting accustomed to our new environment and new tools. After that, we get a little bit freer and a little bit more creative, and we can enjoy that a little bit more. So, all good. See you tomorrow, bright and early, and enjoy your afternoon. Thank you. Bye.
Sir, the class is not found, sir.